Okay, picture this for a second. You're a robot,
Right.
and you're, a top-of-the-line machine, gleaming chrome, fancy joints, a processor that can run a billion calculations in the time it takes me to snap my fingers.
So I'm pretty smart.
Exactly. You're rolling along, sensors humming, everything is perfect.
Hmm.
But then you look up at the sky.
And what do I see?
You just see a gray blob. That's it. A fuzzy gray patch. Now, your sensors are perfect. They see the color, the shape. But what does it mean?
Right. Is that fog? Is it smoke? Is it a rain cloud that's about to short me out?
Or, and I love that this is an actual option for the lecture we're looking at today, is it a meteor?
A meteor, yeah. Just hurtling towards me.
And that is the absolute nightmare for a machine that thinks in just ones and zeros. True or false? There's no rule for gray blob. You just freeze.
But we don't. Humans deal with gray blobs constantly. We make a best guess.
And that's really the gap we're talking about today. The gap between a simple calculator and a truly intelligent agent. The real world is just messy. It's uncertain.
So today we're tackling how AI bridges that gap. We're doing a deep dive into a lecture called Probability Basics for Artificial Intelligence from Dr. Reza Abdali, which was adapted from UC Berkeley materials.
And the big question is, how do you teach a binary machine, a computer, to handle the idea of maybe?
It's a huge mental shift. You have to go from pure logic, this is true or this is false, to inference. This is, say, 70% likely to be true.
It's all about managing beliefs, which is a phrase I just love. Sounds like the robot needs a therapist.
In a way, it does. It's all about managing confidence levels, and the lecture sets this up with two types of information that an agent, that's our robot, has to deal with.
Okay.
You've got your observed variables and your unobserved variables.
Right. Break that down for us. That seems like the foundation for everything.
It really is. Observed variables are your evidence, the things the agent knows for a fact right now.
So like a temperature reading of 72 degrees. Or the camera seeing a red pixel.
Exactly. The hard data, the knowns. But then you have the unobserved variables. These are the things the agent actually cares about, the questions it needs to answer, but it can't see them directly.
So the camera sees the red pixel that's observed.
Yep.
But the question, is that a stoplight? That's unobserved. You have to infer it.
Precisely. Or, to use the more whimsical example from the slides, the agent might know its coordinates on a map, but the unobserved variable is, where is the ghost?
The ghost example is so good. It just perfectly captures it. AI is basically ghost hunting.
It's trying to map the invisible using the visible. And the toolkit for that is probabilistic reasoning. But, to use the tools, we have to learn the vocabulary first.
And that starts with the random variable, which I have to admit sounds like total chaos, like rolling dice.
Yeah, that's a common way to think about it, but it's a bit of a misnomer here. In AI, a random variable, usually a capital letter, isn't chaotic. It's just a formal way of asking a question about something we're uncertain about.
It's like a placeholder for an unknown answer.
Exactly. And each one has a domain, which is just the menu of possible answers.
Yeah.
The lecture gives some really clear examples.
Okay.
You have the variable, capital $3, that just stands for the question, is it raining?
And the domain for that is just true or false.
Simple. But then you have variable dollars for temperature.
That could be more complicated.
Right. The domain could be simple, like hot and cold, or it could be a whole range of actual numbers.
And then there's variable dollars drive time to work.
Yes. The one that causes so much pain.
The domain for that is basically 0 to infinity.
Theoretically, yeah. Let's hope it's not infinity.
And then for our ghost hunter, you have little dollars for location, where the domain is a set of coordinates.
Right. So the AI carves up the world into these questions, these variables, and an event is just a specific outcome, like the temperature's hot and it is sunny.
Okay, so this combination of variables brings us to what the source material calls the joint distribution.
Yes. The joint distribution sounds a bit technical, but you should think of it as the AI's complete map of the universe.
A map of the universe. Why is it so powerful?
Because if you have it, you're basically omniscient. It's a giant table that lists every single possible combination of outcomes for all your variables.
Every possible version of reality.
Every single one. And next to each one, it lists the exact probability of it happening.
Okay, let's use the example from the slides to make this concrete. They use a simple world with two variables, temperature and weather.
Right. Temperature can be hot or cold. Weather can be sun or rain. That gives you 4 possible worlds.
A 2x2 grid.
And the table gives a probability for each. So hot and sunny, the probability is 0.4.
A 40% chance of a good day.
Then hot and rain, that's 0.1.
Muggy, 10%.
Cold and sunny is 0.2.
A nice crisp morning, 20%.
And finally, cold and rain is 0.3. 30%.
And if you're adding those up in your head, 0.4 plus 0.1 plus 0.2 plus 0.3.
It equals 1.0, and that is the golden rule. It has to. The sum of all possibilities must be 100%.
So if the robot has this table, it's all-knowing. It can answer anything.
In theory, yes. It's a lookup table for reality. But, and this is a huge but, this is where the lecture throws a wrench in the works.
The scaling problem.
The scaling problem. That little table was easy. 2 variables, 4 rows. But a self-driving car, it's tracking hundreds of variables. Speed, pedestrians, traffic lights.
Let's say no variables.
Right, no variables, and each one has, say, tossable values. The size of your table, your map of the universe, is $ to the power of net
It's
value.
a lot, which gets big fast.
The big doesn't even cover it. Let's say
Yeah.
you have just 100 binary variables, true or false. That's 2 to the power of 100.
And that number is?
It's roughly the number of atoms in the known universe. You can't write that table down. You can't store it. It's physically, computationally impossible.
So the perfect map of the universe is too big to read.
It's too heavy to hold, exactly. So
Okay.
AI has to get clever. How do you use the idea of the joint distribution without actually building it?
And that leads to our next tool, marginalization.
Right. Or summing out. It's a way to get a simple answer from that giant, complex table by ignoring the stuff you don't care about right now.
Okay, back to our simple weather table. Let's say I only want to know the probability that it's not. Just Pio. I don't care about sun or rain.
Okay, so you look at the table. There are 2 rows where it's hot. Hot and sunny is 0.4.
And hot and rain is 0.1.
To marginalize the weather, you just add those 2 together. 0.4 plus 0.1 is 0.5.
So a 50% chance of it being hot. Simple as that.
Simple as that. You've collapsed the table. You've basically looked at the shadow of the data to get the basic shape instead of looking at the whole complex object.
That makes a lot of sense.
Yeah.
But it still feels a bit static. You know, the real intelligence comes when new information comes in.
Yes. This is where we get into the real heart of it. This is inference. We move from what's the chance of X to, okay, I just saw Y, so now what's the chance of X?
That's conditional probability. The probability of given dollars.
And the traffic example from the lecture is perfect because we all do this in our heads every single day.
Okay, so I'm the agent. I'm trying to figure out if I'll be on time for work.
Right. Before you even open your eyes, you have a base belief. Let's say, given no accidents, you think there's a 90% chance you'll be on time.
Feeling pretty good, 0.9.
But then you observe something. You look at the clock, it's 5 a.m. You woke up early.
Ah, new evidence. That's good news.
Right. So your belief updates. The probability of being on time, given it's 5 a.m., now jumps to, say, 0.95. You're almost certain.
But then I look out the window and it's raining.
And rain changes the whole calculation. Your belief updates again. The probability drops maybe to 0.80.
So my belief went from 90 up to 95, then down to 80.
It's not fixed. It's fluid. It breathes. As you observe new variables, you update your belief about the unobserved ones.
This is what we actually mean when an AI is thinking. It's constantly taking in evidence and updating its internal probabilities.
It's narrowing down the possible worlds. It's saying, okay, we're definitely in a rainy world now, so let's just ignore all the sunny worlds and recalculate.
Okay, but how? What's the actual math? The lecture calls it the normalization trick.
Yes, this is the mechanic. It's a 3-step process. Select, normalize, and divide.
Select, normalize, divide. Let's walk through it with the weather table. Hot sun is 0.4, hot rain 0.1, cold sun 0.2, cold rain 0.3.
Okay.
Now, our robot observes rain. That's a fact. So what's the new probability of it being hot?
Step 1, select. We know it's raining, so we take our table and we throw away every row that says sun. Those worlds are now impossible.
Okay, so hot sun and cold sun are gone. We're left with just 2 rows. Hot rain, which was 0.1.
And cold rain, which was 0.3.
But wait, if you add those, 0.1 plus 0.3, that's 0.4. That doesn't add up to 1.0. We broke the rule.
We broke the universe, so we have to fix it. That's step 2. Normalize. We take that sum, 0.4, and we call it our normalization constant. Let's call it Z.
So Z is 0.4.
That's the total probability of our new, smaller universe where it's definitely raining. Now for step 3, divide. We scale up our remaining probabilities so they fill the new universe.
So they add up to 1 again.
Exactly. So for hot given rain, we take its old value, 0.1, and divide it by our Z, 0.4.
Okay, 0.1 divided by 0.4 is 0.25.
a 25% chance. And for cold given rain, we take 0.3 and divide by 0.4.
Which is 0.75.
And look at that. 0.25 plus 0.75 equals 1.0. The universe is whole again. We've updated our beliefs based on the evidence.
That's so cool. It's like you're zooming in on the rain part of the map, and everything inside that region gets bigger to fill your view.
That is a perfect analogy. That's all conditional probability is.
So that covers the how. But the lectures goes a step further into the why, bringing up Bayes' rule. Now, this can get really math heavy, but what's the big idea here? Why is it so important for AI?
It's important because it lets you flip the direction of your reasoning. It lets you go from cause to effect, or more importantly, from effect back to cause.
And the medical example they use is perfect for this. Meningitis and a stiff neck.
The classic diagnostic problem. See, a textbook gives you the causal probability. It tells you if a person has meningitis, what's the probability they'll have a stiff neck?
That's text meningitis.
Exactly. But a doctor in an emergency room has the opposite problem. A patient walks in with a stiff neck. The doctor needs to know the diagnostic probability.
What's the probability they have meningitis given that they have a stiff neck?
Right. And Bayes' rule is the formula that lets you calculate that second number using the first one. It connects them.
But the slide makes a really interesting point here. Meningitis is super rare.
Very rare. But stiff necks are incredibly common. You slept wrong. You looked at your phone too long.
So when you do math, even with a stiff neck, the probability you actually have meningitis is still tiny.
Extremely small, like fractions of a percent.
Which raises the question, if it's so unlikely, why does the doctor even worry about it? Why order the tests?
And that's the bridge from just probability to decision theory. It's not just about what's most likely. It's also about the cost of being wrong. If the AI or the doctor assumes it's just a common stiff neck and it's wrong, the patient dies. The cost is catastrophic.
So it's not just about the probability. It's about probability multiplied by the stakes.
Exactly. Even if there's a 0.0001% chance that gray blob is a meteor, the cost of being crushed is so high that you might want to, step aside. You don't ignore a tiny probability if the outcome is that bad.
Wow. It's incredible. We started with a robot afraid of a cloud, and we've ended up at the core of how we make life or death decisions.
It's all the same mathematical framework.
So just to recap for everyone, an AI sees the world as a set of uncertain questions or random variables.
And it has this theoretical master map of all possibilities, the joint distribution.
But since that map is impossibly huge, it uses tools like marginalization to get simpler answers.
And conditional probability, using that select normalized divide trick to update its beliefs when it gets new evidence.
And it all comes together to allow a machine to reason, to infer hidden causes from visible symptoms, and to weigh risks. It really turns a calculator into a reasoner.
Well said.
I want to leave you with one final thought on this. The lecture talks about the agent observing variables. The robot sees the rain, the doctor sees the stiff neck.
Right, the evidence.
But in our world today, we are the variables being observed. We are the data points, our clicks, our searches, our location. Every time we pause a video, we are the evidence being fed into these massive AI systems.
That's a really good point. We are the observed variables.
So if we're the observed variables, what are the unobserved variables about us that they're trying to calculate? Ideally, it's just, does this person want to buy this book? Or what movie should we recommend?
The simple stuff.
But when you think about that ghost example, the AI trying to find the ghost in the machine, you have to wonder, what else are they inferring? Our moods, our political leanings, our future actions. They're building a probability distribution for the ghost that is us.
That is a profound thought. We're the input, and a model of our own mind is the output. Let's just hope their joint distribution table has a row for human would like to be left alone now.
And let's hope the calculated cost of bothering us is high.
Hey, right.
Thanks for listening to this deep dive. Next time you find yourself making a judgment call, ask yourself, are you marginalizing or are you normalizing?
And hey, seriously, if you have a stiff neck, go get it checked out.
Always good advice. See you next time.